Hello and welcome to episode number 13 of CS350 Online. I'm your host as always, Leslie Eisted, and in today's episode we are going to continue our discussion of virtual memory, but today we're going to focus more on some of the realities of implementing paging and how virtual memory is implemented in OS 161, which will help you understand some of the interesting issues that you might be encountering with assignment 2, and will certainly help you with assignment 3 for those of you who decided to go ahead and get started with that. Just a couple things to announce is that you should really get started on assignment 2 if you haven't already. It's not that the code is particularly difficult to implement, it's that debugging it is absolutely brutal. And you might spend, 8 hours writing the code and 3 weeks trying to debug it. The most common mistakes I see being made in assignment 2 come down to things like deadlock and race conditions around the combination of wait, PID, and exit. And what it usually is when you go to check whether your child is still alive or not, you actually need to acquire the child's lock because the child could be terminating at the exact point in time where you are checking their status. And so it's really, really important that those variables are protected by the lock and your check is protected by that lock. So just keep that in mind. The other thing I wanted to say is assignment 1, of course, has been graded and returned, and I know a number of you have had some questions about grading. Please direct your grading questions to our IAs. They're absolutely wonderful. There's Ryan and Emilios. And they generally handle things like the marking scheme, and they'll know what marks got removed for what particular reasons. So they'll be able to help you there. And if they have anything that they are confused about or they need a little extra help, they will reach out to the instructors to make any final decisions. But your first line of attack for grade questions should be to go to them. All right, so the OS of the day today is one that you've probably heard of for once, and that is a BSD. Now, BSD stands for Berkeley Software Distribution because what's interesting about BSD is that originally it wasn't an operating system. Originally, this was just a package of extensions that were provided to Unix version 6 called 1BSD, and it was actually a bunch of Pascal software to help students learn the Pascal language. It was an editor called EX, and there was a new shell and some new commands, end of game. So it was just little extensions to Unix. Now, for those of you who haven't heard of the Pascal language, it's very C-like, I want to say. So I used Pascal long time ago. It's hard to describe because it's not a language people use much anymore, but it's very C-like, and it was very, very popular in the 80s and 90s, certainly. Like if you were to go through like the classified pages of a newspaper, because it's early internet days, people didn't really do that, but you would see like a ton of Pascal jobs. There's some interesting ambiguities in the language, but it's a fun language. Anyways, so the first distribution of utilities was really successful, so they created a second one called 2BSD, which included VI for all the VI people out there. Yay! And it also included C shell, not to be confused with that thing that you use in CS136. I mean the real C shell, as in CSH, which is what people used to use instead of Bash or whatever. And then 3BSD was actually its own operating system, and they were originally going to call it VM Unix because they were originally going to offer a implementation of virtual memory for VAX machines, which at the time, VAX was super, super popular. And this was a really successful DARPA-funded project. So DARPA funding, if you're not familiar with, is like American military funding, and it's really big deal. It means that, federal U.S. government really believes in what you're working on and wants you to succeed with whatever you're doing. So 3BSD was actually, the reason why they got a lot of DARPA funding was actually because of the networking utilities that they were building into it. So it's the first Unix based operating system that had internet protocol stacks and sockets to actually make network transfers really simple. That's kind of technology we still use today, and so yeah, that's a pretty big deal. So this OS was actually released in 1978. It was originally produced for a PDP-11. But BSD is actually still under active development, and it's obviously still around. So there's like FreeBSD and OpenBSD and NetBSD and all those things like that. But so many operating systems that you use today are actually derivatives of BSD as well. So if you have a Mac, you are actually using a BSD variant. And if you use SunOS or Solaris, that's also BSD. So there are many, many BSD variants. And I mean, we can go back in time. I showed you this lovely thing here. So to show you where Mac OS actually stands in this, so you've got Unix version 6, and then you can see BSD 1 and BSD 2, and then we've got BSD 3 and 4, and BSD 4.2, BSD 4.3, and off of BSD 4.3, you can see an operating system called NextStep or OpenStep branches off of BSD 4.3, so there's a derivative, and that turns into Mac OS X Server, which turns into Mac OS X. So there you go. So why does a lot of Unixy things work in Mac OS? Well, because it's based on Unix. Although Apple's obviously made a lot of their own changes because that's what they do. Okay, I'm going the wrong direction. All right, so what I'd like to do then is at the end of our last class, I introduced a couple sample problems. So let's bring them up. I can find them. I'm sure I can find them. So here we go. So this is the paging PDF file from the extra sample problems we post as part online, and they're in that one Piazza thread. So let's actually go through these different sample problems and actually solve them. So I'm just going to open OneNote here so we can type right. And let's make a new page. Some nice lined paper, and let's try to write neatly. Okay, so the first thing we look at is this is a single level paging problem. So if we take a look, we have a page-based virtual memory system. We have 32-bit virtual and physical addresses, so up to 4 gigabytes of memory, and the page size is 2 to the power of 12 bytes, which you should memorize is 4 kilobytes. So there's a process P that is running, but P only uses 128 kilobytes of virtual memory. And we're going to assume that P's address space, instead of being allocated as code data and then stacked somewhere else, we're going to assume it's contiguously allocated. So one contiguous block. So here are his part of P's page table. So you can see page 0, frame mapping, and valid bits. So here's some questions. So we want to know what is the total number of entries in P's page table. Now most people get this question wrong because most people will say, okay, well, 128 kilobytes, which is the size of P's address space, how many pages is that? That's not what the question is asking. The question is asking how many entries are in the page table. And the number of entries in the page table is not related to the size of the address space. It's related only to the size of virtual memory. So for question 1, let's make sure we have the right thing to draw with here. So for question 1, we take the size of virtual memory, which is 2 to the 32, and we're going to divide it by the page size, which is 2 to the 12. And that's going to give us 2 to the power of 20 entries. We'll just say PTEs. So remember that. The number of entries in the page table is not related to the size of the address space, but related to the size of virtual memory. So let's go to the second question then. Now we want to know how many entries are valid. Now this one here is related to the address space. We know that there are 128 kilobytes actually used. So how many pages does that work out to be? So we have 128 kilobytes divided by 4. And that gives us 32. Now we again are assuming that those 128 kilobytes are contiguously allocated. And so in that case, there are 32 valid entries. Okay, so that's not too bad, right? Now the second question too. Funny typos that show up. By the way, this is an old midterm problem or old final problem. So we want to know what is the physical address that corresponds to each of these virtual addresses. So we want to translate these addresses. So I'm going to write the addresses down here, and then I'm going to scroll back up to the page table so that we can actually do the translation. So let's do... Now, in this case, we've drawn all the leading zeros, but remember that even if they are not visible, they are still there. It's nice when we draw the leading zeros, but I'm not going to lie. Sometimes we're lazy and we don't draw them. Okay. 0, 0, 0, 4, 6, 6, 4. Okay, so in order to do the translations here, the first thing that we need to do is we need to actually figure out how big the page number is. So how many bits do we need for a page number? So... looking back up here, we know that the number of bits for page number is equal to the log base 2 of the number of page table entries. So this is going to be the log of 2 to the 20. So we end up with 20 bits for our page number. Now, what's interesting to remember is that each hex digit is 4 bits, so this is the upper 5 hex digits. So just keep that in mind. All right, so let's write this down by our page number. So the page number for the first one, so let's take the first 5 hex digits, is 00001. So this is on page 1. And then the next one is on page 0. And the one after that is on page 4. Oops, I wrote as 1 when I meant 0. Now let's look at the offset. The offset is equal to the lowest bits, that is the length, the log of the page size. So it's going to be the lower 12 bits or the lower 3 hex digits. So what we can do is we can just split each address into 2 parts. There's part 1 and there's part 2. And what's nice about this particular example is it's a nice multiple of 4, which means that we don't actually have to decompose this address into binary to find the answer. So my offset here is A60, and for this one is FB5, and this one here is 664. So that's fun, right? Okay, so now let's do the physical address. So the physical address, let's do it in a different color. So I'm going to look up page number 1, and I see that maps to frame 235. So that's going to give me 2, 3, 5. And then I'm going to drop in my offset A60. So there we go. And here you'll notice that I've actually dropped all the leading zeros because they don't need to be there, even though they are. I just don't like writing them. I often write the wrong number, that's why. Okay, so let's look at the second one. So on page 0, we see that that one is also valid. So we're going to end up with 2, 3, 4, FB5. And then for page 4, which is the last address, we see that that maps to frame 4, and that's totally valid, by the way. That can happen. We end up with the physical and virtual addresses actually being the same. And that can happen. That can absolutely happen. Right. So that's the third question. The final question asks, if the page size is 16 kilobytes instead of 4, how many entries would there be in P's table, and how many bits would be used for the offset and for the page number? So let's actually take a look at this. So Q3. So if we have 16 kilobyte pages, that's equal to 4 times 4 kilobytes. So that's equal to 4 times 2 to the 12. So that's 2 to the 2 times 2 to the 12. So that means our page size is 2 to the 14. Okay, so that should be fairly straightforward math. And then to figure out the number of PTEs, then we're going to do 2 to the 32 divided by 2 to the 14. So that's going to give us, instead of 2 to the 20, that's going to give us 2 to the 18. And then the number of bits for the offset is equal to the log of the page size. So that's 2 to the 14, which means 14 bits for the offset. And the number of bits for the page number is now the log of 2 to the 18, which means we need 18 bits for the page number. So there you go. That is the single level paging problems solved for you. All right. So let's create a new page, add some lines to it, and let's look at the second problem we left you with, or the second page. The second one is multi-paging. This one's a little bit trickier. Well, the first questions are easy, but the last part is actually quite tricky. So again, we have the setup for the virtual memory here. We've got, instead of 32-bit virtual and physical addresses, now we have 64 bits. That's fine. Our page size is now 2 to the 20, so 1 megabyte. And each page table entry is now 2 to the power of 4 bytes. So, and this is going to be multi-level paging, so we're making the requirement that each individual page table at each level has to fit within a page, which means that it has to be less than or equal to a page size. So we want to know how many bits of the virtual address are used for the page offset. So this is actually really easy. So for question 1, page offset. That's just the log of the page size, which is 2 to the 20. So that means we have 20 bits for the page offset. And that is not related to how many levels are in the page table. The number of bits that we use for the offset is always related to the page size and the page size alone. All right. The next question is, what's the maximum number of entries in an individual page table? Okay. So the number of entries we can fit into a page table, if the page table is going to be the page size divided by the PTE size. So in this case, we've got 2 to the 20 divided by our PTE size, which we've been provided as 2 to the 4. So that's going to give us 2 to the 16 entries per page. Okay. That's not so bad. The third question is, how many levels are going to be in the page table? Well, we have a magical formula that we provided you before. So the number of levels is going to be the ceiling of V minus the offset bits divided by the page bits. Page number bits. And we can get the page bits. how many bits we need to index the page table, is the log of the number of entries. So it's 16. And so we end up with the following. We get 64 minus 20 divided by 16. And if you solve that out, you end up with 3. We need 3 levels. Now, you may have a hard time picturing how that works. What's interesting is it doesn't divide evenly, but if you look at our 64-bit address, so here's our 64 bits. We're going to set 20 aside. This is our offset. And we're going to take 16. And then we take 16. So moving this way. And then we end up with 12 left over. And since 12 is smaller than 16, this is totally valid because the page table would be smaller than a page, which means it's valid. So we end up shoving the fewest bits for the page number into the directory or the root of the tree. Now, there are different schemes that try to balance this out. We're not going to use any such scheme, and you can always assume that I am going to put the smallest number of bits in the root. That's just how I prefer to do it. If we have a question about how this is laid out, we will give you instructions on how to solve it. All right, so now comes the hard question. So suppose we have some process with a contiguously allocated address space, and it uses the first 128 megabytes of virtual memory. So its virtual address range goes from 0x0 all the way to whatever 2 to the 27 minus 1 is. Okay, so we want to know how many page tables at each level exist and how many valid entries will be in each table. This is a really tricky problem, but it's actually, if you think about this, it's not that bad. So the first thing we note is that these are the valid addresses. This is our valid. And what that means is that every valid address is of the form. Now I'm going to have to do a little calculator here because I don't know what 64 minus 27 is off the top of my head. It's too early in the morning. Okay. So the upper 37 bits, all 0. And then the lower 27 bits may be not 0. Okay, so if we look at all the valid addresses for this address space, that's the format they have. And that actually tells us a lot of information. A lot of information. Because if we look at our layout of our address that we just computed, sorry for the horrible drawing. We've got 12, 16, 16, and 20. So this means that these 20 plus these 7 bits of the lowest level table are going to be non-zero or could be non-zero. But I know that all of these bits up here, all of these bits, all of them are all zeros. So every valid address has all 12 of these bits 0. And every valid address has all 16 of these bits 0. And every valid address has these 9 of 16 bits are all 0. And that actually tells me everything I need to know. Because I know that I always need, at the top level, I always have only one table. However, how many valid entries are there? Well, since I know that every valid address has the first 12 bits set to 0, there can only be one valid entry. Because all of the valid addresses start with the same bits, same 12 bits. Since there's only one valid entry in the top level, then our mid level has only one table as well. And since all of those bits are also 0, I know there's also only one valid entry in it. Which means at the bottom level, there's also only one table. But it has more than one valid entry because the lower 7 bits are used, so 2 to 7 valid entries. So that's kind of a way of picturing how you could do this. There are other ways to do it. If you want a challenge for yourself, try this where the address uses 39 bits. And see what you get. Okay, so that's a fun thing you can try on your own. And if you post the answer to Piazza, we can take a look and let you know if it's correct. All right, so those are all of the sample problems that we introduced in our previous episode. I apologize, I'm still doing the whole morning sickness thing for a few more weeks. We'll try to get through it. All right, so let's go back to our course notes. So we finished talking about the different methods that we use to actually translate our virtual addresses. And now what we need to talk about is just remembering who does what. So remember that the kernel is going to manage the MMU. The MMU is a piece of hardware, remember? And so it has to manage the MMU because on a context switch between different processes, the translation information for the process is going to change. And so the kernel is responsible for updating the MMU with the new processes information to perform the correct translations. The kernel is going to be creating and managing page tables. It's also going to manage the physical memory itself. And if there's any exceptions raised by the MMU, the kernel will also handle that. So the kernel does a lot, but it doesn't do it very often. The MMU, the memory management unit, which is the hardware, actually does all of the actual translation. So it's going to take each virtual address and translate it to each physical address. And there could be anywhere from at least 1 to as many as 3 or 4 translations happening per instruction. So the MMU does a lot more work. And then it's going to check for and raise exceptions wherever they are needed. So that is, if a page table entry is invalid, then it's going to raise an exception. If you're trying to write to a piece of read-only memory, it raises an exception. It doesn't know how to handle those exceptions because that's the role of the kernel. So let's just remember it. Okay. We have a little problem, though. This is normally when I start walking across the room, but you know, I'm not going to get up from my chair to do that. So anyways. So let's suppose that we're using paging. And so for each address translation, the MMU is going to have to use the page table base register to find a location in RAM where that page table entry is. So you're at the MMU and you've got to translate the program counter. So you go to RAM, which means you're leaving the CPU, you get your address, and then you come back. You perform your translation. And let's suppose it was just an add. So then you have a subtract instruction. So you go back to RAM to get the program counter again. Well, let me show you what I mean. I can actually do this a little bit better by actually drawing it out. So we'll open OneNote back up again. Let's get a new page. What I'm saying, what I want to show you, is that if you have a bunch of instructions like this, sequential instructions, which, you know, for the large part, your code does look like a bunch of sequential instructions aside from branches and jumps. But you've got a lot of things like this. Add, sub. Oops. That's good spelling. You've got a bunch of sequential instructions. Now, these instructions here, I've got, what have I got? 1, 2, 3, 4, 5, 6, 7, 8. These instructions, the probability that these live on the same page is pretty high. So these instructions all probably live on the same page. So what's going to happen is for each of these instructions, I am going to go to RAM to get the same page table entry at least 8 times. I don't know if you know much about performance and hardware, but if here, this is your CPU, your RAM is all the way over here. It's like, let's suppose that you were sitting down and you're playing a game, and I don't know what game you like, but games that I like are things like the original Unreal Tournament. I like Red Alert 2 and the expansion Yuri's Revenge, and I was always a big fan of Tiberian Sun. Yes, I know those are very old games, but they're very, very fun PC games too. And I guess I've played a lot of Warcraft 3 as well. But if you're sitting down to play a game, this would be like getting something from memory that's like on the CPU is like reaching your hand out to the other side of your desk and grabbing your drink. Getting something from RAM is you having to get up from your computer and walk to your fridge and get yourself a drink. One of those things takes a lot more time than the other. So what we're essentially saying here is for each of these address translations, we have to go to RAM. We have to walk to the fridge. That's going to add up. Now that's just with single level paging. Now let's imagine we're doing multi-level paging. And if we have like 4 levels, which by the way, if you're looking at modern implementations of virtual memory on the computer sitting in front of you, the page table is usually 4 levels. So if I wouldn't be going to the page table, to RAM once. In order to translate each address, I would actually have to go to RAM 4 times. So that's you sitting in front of your game, your favorite game, and you have to walk to the fridge 4 times separately to get your drink. Like the first time you walk into the kitchen and you open the cupboard door, and then you walk back to your seat because you forgot what you were doing. And then you walk back into the kitchen and you grab the cup out of the cupboard and you put it on the counter. And then you walk back to the game and then, oh wait, I was getting a drink. So then you go to the fridge and you pour yourself a drink and you leave it in the kitchen and you walk back to your game. And then, oh wait, I was getting a drink. So then you walk back to the kitchen and finally bring your drink back. I mean, that took a really long time. That's just silly. Okay. So paging has additional problems in the fact that we're going to have to go to RAM a lot. And so we want to solve that problem. Good news is we can solve this problem. Okay. So what we want to do is we want to have some memory in the memory management unit that we can use to cache some of these page table entries. So we can reduce the number of times overall that we actually have to go to RAM. Sorry. It's going to sound weird, but actually talking makes me very nauseous. So good news is your MMU actually does have an onboard cache for specifically this purpose, and it's not called a cache, it's called the translation look-aside buffer, or TLB, and it's a very small cache which is used to store page-to-frame mappings. So what's going to happen is instead of for each address translation going to RAM to grab the page table entry, first we're going to check the cache. We're going to check the TLB, and if it's in the TLB, that's just you reaching across your desk to grab the drink instead of having to go to the fridge 4 times. So it's really good. Now there are 2 ways that we can actually implement a TLB. There's a hardware managed TLB and a software managed TLB. The hardware managed TLB is going to definitely be faster because generally when we can do things in hardware, that's going to be faster. And here's what happens is, so when you have an address to translate, the first thing we do is we look at the TLB, and if there's an entry with that page in frame, or with that page, then we have what's called a TLB hit. We get the frame number from the TLB entry, we perform the address translation, and we're happy. If, however, there's a TLB miss, that is, it's not in the TLB, then the hardware has to go to RAM, get the page table entry, add it to RAM, or add it to the TLB, and then it can return the frame number. Now, the issue here is that when you try to add something to the TLB might be full because it's not a very big cache, and so the hardware is going to have to do cache eviction strategies to choose an appropriate entry to kick out of the cache for your new one so that you can actually use it. Now, here's the interesting thing. If we do this in hardware, it is fast. But unfortunately, it means that the hardware actually has to know the format of the page table entry, which means that your hardware is going to be dictating to the software developer the format of the page table entries. So that's actually not something that programmers really like, is having hardware tell them how to do things. Fast, but a little restrictive. The alternative approach is to do a software-based software managed TLB. And the idea is, if there's a hit, there's no difference. But on a miss, a TLB miss, instead of trying to find the entry itself, the MMU just raises an exception. And then the kernel responds to that exception and says, okay, you had a TLB miss. That means something is missing from the TLB. So then the kernel is going to look up the page table entry, and the kernel is going to be responsible for putting that entry into the TLB and performing any cache eviction strategies on the TLB. And then the kernel doesn't do the address translation. The kernel is going to return from the exception, and then that translation is going to happen again. So it's going to repeat, and this time it will actually succeed. So that's a software managed TLB. It's a little slower because we do have to throw an exception and the kernel does have to handle the thing. But because it's being managed by the kernel, the page table entries can be whatever you want. The kernel can do however it wants. And I think you'll find that most systems are doing a software managed TLB, and OS 161 also does a software managed TLB. And you've probably noticed this because if you're working on assignment 2, you may have noticed that you get TLB miss on store, TLB miss on load exceptions. Software managed TLB. Okay. So let's actually look at the MIPS R3000 TLB. So remember that we're using a simulated MIPS R3000 chip, which is a real chip. This is not a made-up piece of hardware. MIPS is a real thing. It's not so popular anymore. ARM has really taken over as the latest, greatest, small, RISC-based CPU, but MIPS used to be an ultra-popular RISC chip, and I have actually worked on MIPS chips in industry. In fact, a lot of my co-op jobs were doing things with MIPS chips. Kind of fun. So the R3000, by the way, was like the CPU in like a PlayStation 1, and it was a coprocessor in a PS2. So it's in things that you've used before. So the TLB entry on the MIPS R3000 is 64 bits, so 2 words. The high word, the upper 20 bits, corresponds to the page number. And in the low word, the upper 20 bits corresponds to the frame number. And then there's a bunch of flag bits that keep track of write permission and whether it's valid and so on and so forth. Now you'll notice that 6 bits are allocated for the PID, but it says this is not used. But I'd like to talk to you about what that could be used for, what that was intended for. So here's the thing. The cache, this TLB, is only meaningful for the current process. And if we do a context switch between processes and we don't clear the cache, then we would be using some other process's address translations for us. And that doesn't make sense. I mean, it's a security breach and it's just absolutely goofy. We'll get garbage behavior. So typically speaking, not typically, always, on a context switch, we clear the TLB. And in OS 161, you do that with the AS activate function. That's going to clear the TLB. And so we clear the TLB whenever we do a context switch. Or when we change the program that's running, we're going to clear the TLB. And that's because this field isn't used. What this field can be used for, this PID field, is you can actually assign the PIDs to the TLB entries. And then the idea is that the CPU would also keep track of, have a register that would keep track of the PID of the current process running. And then the idea is when you're doing an address translation, the MMU will know the PID of the current process, and it can use the TLB entry to only look for matching entries for that process. The advantage here is that we're not clearing the TLB. So we have something called cache affinity, which means that if you run and then somebody else runs, and then you run again, there's a chance that some of your entries are still in the cache, which means you get a bit of performance boost the next time you run. So this lets us have cache affinity. It actually improves the performance a little bit. But this has not been used. It's not used in the MIPS R3000. And what's really, really interesting is that this field exists in the Intel and AMD MMUs as well. There is a PID field in their TLB entries. And up until the last few years, it also wasn't being used. And then I'm not sure if it was Meltdown and Spectre that actually caused them to start using this, but they realized that they actually needed to start, instead of clearing the TLB each time there was a context switch, they decided, for security reasons, we should really start using this PID field to check to make sure that the process that's requesting the address translation actually belongs to this TLB entry. So this is something that we do not use in OS 161, but in very recent years, we have actually started using the PID field. So that's kind of cool. All right, but we're not using it. So you still have to call AS activate every time you do a context switch. So just to wrap up paging, paging is going to solve the problem of external fragmentation because every single allocation is going to be exactly the same size. There is internal fragmentation, but it's so minuscule we don't care. Like, honestly, if we waste 3 kilobytes and you've got 64 gigs of RAM, nobody cares. Honestly, nobody cares. And even like if I'm thinking back to like my first 486 that I bought and I had 30 megs of RAM, considering I could only run like 2 processes at a time, I wouldn't have cared about 3 kilobytes of RAM being wasted there either. So it's really not a big deal. And to solve the problem of the wasted time going to and from RAM to do the page table lookups, we have the TLB to help improve the speed. And we can have a hardware managed TLB that's going to do everything in hardware and a software managed where we'll get the kernel of the OS to actually solve that problem. Now, what's really interesting is that paging has actually been around for a really long time. So in the late 1950s, that's actually when papers were started to be written about it. And in the early 1960s, that's when people actually started to do it. And I'm going to tell you a little secret, which we'll talk in more detail about. But like the first versions of Windows and Mac OS didn't even use virtual memory. They just used physical addresses. And it wasn't until after Windows 3.1 that Windows even used paging. Like they used segmentation. And it was fine. Because for the speed of the processes and the way that was used at the time, it wasn't a big deal. So yeah. Windows and macOS were actually pretty late adopters of this technology, considering when it was invented. And as I mentioned before, currently we use 4-level paging, but the Linux kernel actually, with 48-bit virtual address, the Linux kernel is currently supporting 57-bit virtual addresses, which would be a 5-level table. Now, I don't know why they used 57, because it's not an even number, but that's just weird. Anyways, it's interesting. That's the future. All right. So, how does virtual memory in OS 161 work? Well, number one, I'm going to tell you it's called dumb VM because it's really dumb. And you're going to fix it in assignment 3. So right now, MIPS uses a 32-bit virtual and physical addresses, and it has a software managed TLB. And the function which handles all of the TLB misses, which you may be familiar with now, is called VM fault. And even though the MIPS architecture uses paging, OS 161 actually uses segmentation. And you may be like, well, if it uses segmentation, then how is the hardware using paging? It's actually pretty easy to shove segmentation down the throat of a paged MMU. The trick is, instead of letting each page of the address space be allocated to it, mapped to whatever frame of physical memory, we just make the requirement that, the code segment, which is 12 pages, maps to contiguous 12 frames. And that's how you shove segmentation down the throat of a paged MMU. And that's what OS 161 does. So OS 161's implementation actually has external fragmentation. Problem you'll fix later. Now, all of the details of the address space for OS 161 are contained in the structure address space. And there are 3 segments to our address spaces. There is the code or text segment, there is the data segment, and then there is the stack segment. So in our address space structure, we can keep the virtual base address, so where in virtual memory does each segment start, where in physical memory, so this is the offset for the segment, does that segment start, and then we keep track of the segment size as a number of pages. So there is going to be some internally wasted space because we are allocating things in terms of pages, but there's also external fragmentation. So VBase, PBase, and NPages 1 are all going to be the code segment. And then VBase, PBase, and NPages 2 are the data segment. And then stack PBase is going to be the stack. Now you'll notice we don't keep track of the virtual position of the stack, and we don't keep track of the size of the stack in the address space. And the reason is the stack is in the same place in in everybody's virtual memory. And the size of the stack is also the same for every process. So those are actually macro constants in the operating system. And the stack, its base address is user stack, and we'll show you that address in a minute. And the size of the stack is set to 12 pages. So our maximum stack size is 48 kilobytes. Its page size is 4 kilobytes here, most common page size. So how does dumb-VM then translate an address on a TLB miss? Okay. So this is actually a snippet of VM fault. This is code right out of there, and I know I've trimmed out some of the details. But here's user stack, so that's the base address of the stack. You can't actually use this address, but you can use the one above it. And so that's the constant for the user stack. That's the constant for page size. And there's dumb-VM stack pages, so that's the length of the stack. What we do first is we compute the base address, so the low and the high for each of the segments. So this is getting the low address for the code segment, and this is the high address for the code segment. So the high address is the base plus the number of pages times the page size. And then we do the same for the data segment, and the same for the stack. So we get the base of the stack, which is going to be user stack minus dumb-VM stack pages times page size. So it's going to be this address here. So the low address actually ends up being, just looking for the number because I don't want to do the math off the top of my head because I don't like to do that. So what you end up for stack base, that's not going to be good. It did not mean to open resolve. Go away. So stack base is 0x7FFF4000. Okay? So that is stack base. So that is the low address for the stack. And then the high address for the stack is just user stack. Okay, click on the right thing here. Okay. So what we're going to do is we don't actually have like a separate segment number. How OS 161 does it is it checks, are you between low and high for the code segment? If you are, then here's how we translate the physical address using regular segmentation math. And if you are not in the range for the code segment, then we check if you are in the range of addresses for the data segment. And if you are, we use the regular segmentation math to translate that. And if you're not in the data segment, then we'll check the stack segment. Are you between low and high there? And if you're not there, then you're not a valid address. So it's a pretty crappy way of doing it, but this is how OS 161 does the translations for address. And then what ends up happening is later on in the file, it will translate this physical address to a page number, which it will then update the TLB with, and that happens just below this code. So I'm going to, let's do a few examples of actually translating OS 161's lovely, lovely addresses. So let's open up our notebook again. We're just going to do process 1, and I'd like you to do process 2 on your own for practice. It's important to get practice. So, virtual address. So, I have 40004. These are V addresses. Okay, so I know that this, just by looking, is going to be in the code segment because I've done this problem a million times. But if we look over here, we have V base 1 is 400,000. So this is greater than 400,000. And this is also smaller than the limit, so the top, which is going to be 400,000 plus 8 times C1000. So we know we're in the limit there. So this is a code segment. So to perform the address translation, we are going to subtract the base address, which is going to be, so we're going to minus, and that's going to give us our offset of 4. And then to the offset, we add the physical base address, which is 20000. So we end up with the physical address for this one as being, there we go. Now for the next one, I can look at it and I see that it probably is going to be in, it's definitely not in the code segment, and I know it's not in the stack segment. So if it's in any segment, I know just by looking at this table here, it's going to be in the data segment. And I see that indeed, since the size of the data segment is going to be 16 pages, remember, because that's 10 in hex is 16. So that's 16 times, well, you can do the math there. So I know that this is data segment. And again, you should compute the stack and the base on your own. I'm ignoring that. So what I do is I subtract, to get the offset, I subtract the virtual base, which gives me the offset as 91A4, to which I add the physical base address, which gives me the physical address of 891A4. That's not bad, right? Now the next one, this one is looks like a stack address to me. So I ask myself, is this between, remember the stack base is, and the stack top is this here. So is that address in the range? It is, so this is a stack address. So I am going to subtract the base. So I'm going to get, and then I add the stack base, physical base, and I'm left with the physical address for this one as that. And then the final address I see as 7FFF32B0. Now I know that's not code and I know that's not data, and if I look at this range that I have over here, I also see that it's not in that range, so I know that this one is an exception. This is an invalid address. Ta-da, we're all done. So I want you to try that with process 2 on your own. And if you have any questions, of course, please do post them to Piazza. All right. Now, one of the questions is, so where does OS161 get this information from? How does it know where to put the data segment in virtual memory? How does it know where to put the code segment in virtual memory? How does it know how big those segments are? Well, actually, because all of that information is actually contained in the binary file. So if you look at the binary files for OS161, they're this thing called ELF, executable and linking format, which is very similar to what you had in CS350. But the header information in the binary file actually contains all of the information you need to actually create the address space. So what we can do is I actually want to show you an example of this. It's going to take me just a minute. Let's make sure we're running bash. And I need to... So now I should be able to run a CS350 object dump. And this is always the problem I run up against, is that it can't find it. There we go, test pin sort. So what CS350 object dump does is this is actually just our version of object dump, and I'm using -H to print out the header of the binary file. And it's in the header of the binary file that actually tells us everything about the code and the data segment for this program. So it's the compiler that actually figures out how big the code segment needs to be, and it's the compiler that figures out how big the data segment needs to be. Now you'll notice there's nothing about the stack in here because the stack is going to be dictated by the operating system and not the compiler. Now why might that be? Well, we can estimate in the compiler how much space we need for the code because we compiled the code. We know how big it is. And the same for data. We can estimate that. But the size of the stack, it really depends on the execution of the program. And you could estimate that for many programs, but it's going to be for something like Photoshop or Resolve, it's really dependent on what the user is doing. So the operating system has a tendency to do that. And also because the operating system wants to have control over putting how big the stack is to control, hey, you should put this in the heap, not the stack. So things like that. So what we have inside this file in the header is the information about the code and the data segment. So here you can actually see this first segment here. This is the code segment of the sort program for OS 161. And it's going to tell us where in virtual memory the code segment has to live. And this is, something that most people don't realize is that compilers and operating systems are actually really tightly integrated, and that when you have an operating system, there's going to be a lot of specifications that they have to provide to the compiler developers because the compiler developers have to make sure that the binary files that are being produced are compatible with the operating system. So those expectations have to be met between them. So there's a lot of collaboration between the two developers. We know where our virtual memory is going to live. And we know also how big it is, so that tells me how big this segment needs to be. And it also tells me information like where in this file can I find it? And then it's going to tell me that this segment needs to be read-only. So there's my code segment information. It's in the binary file. Now, a part of that we also get, this is constants. So this is going to be where the constants live in virtual memory, how big they are, where to find them in this file. Now, OS 161 actually combines these two into the code segment. And then the data segment is down here. So you can see here it's not mapped as read-only, it's marked as data. Here's where to put it in virtual memory. Here's where to find it in the file. Here's the size of it. All of the information we need to create the address space, aside from the stack, is actually found in the binary file of the program. So that's really cool, right? So the ELF file contains more information than that. It's also going to tell us things like where's the entry point for the program, i.e., what is the address of main in the code segment, because when you load a program, you need to know what is the address of the first instruction, because when you actually go and you start executing that thread, we need to know where's the beginning of that thread's sequence of instructions. And the ELF file contains information that's like symbol tables, section descriptors, anything that's useful for things like debugging, linking, and so on, and loading. So there's all kinds of other information located in that file. So again, just to reiterate, all of the information we need except for the stack comes from the binary file. The stack is dictated by the operating system. And in OS 161, it lives in the middle of the virtual memory range, and it is 12 pages. Now, what's really, really interesting you're going to learn is that the stack is actually located in the middle of virtual memory, not just for OS 161, but also for Mac OS and Windows, and any GNU Linux-based distribution. It's kind of weird, isn't it? There's a reason for that, though. I'm not going to get into it today. We might actually end this episode a little early because I don't want to start that topic. So, and the size of the stack is also dictated by the operating system. That's not just true of OS 161. It's also true of the operating system you're using right now. And if you don't believe me, try to create some really big stack things, and you will find there is actually a maximum, and it's not that big. It's only like 1 or 2 megs. So it's actually quite small. So your OS dictates the stack size. So that's kind of a fun bit of information. Now, where does OS 161 actually load all the contents from the ELF file into the address space? So there are various address space functions for creating each of the segments, which will use the header information from the ELF file to create the appropriate segment size. But the actual loading happens in a magical file called load ELF. So load ELF is where we actually load the binary information into the address space. All right. I didn't want to start this right now, but you know what? Let's do it anyways, because we still got lots of time. So the last topic before we go to my favorite part of virtual memory is virtual memory for the kernel. So we know that we keep the user program in virtual memory now, and we see how that isolates processes from each other and from the kernel. But we also want to keep the kernel in virtual memory, which kind of introduces a little bit of a problem, because the kernel of the operating system is responsible for implementing the virtual memory. So how do you have the kernel operate in virtual memory during boot if it's responsible for implementing virtual memory? We call that the bootstrapping problem, and that how that's solved is architectural specific. In OS 161, it's actually solved pretty easily. And then we have the sharing problem, which is if the kernel is also in virtual memory, then how do you distinguish between this is a virtual address for the user process and this is a kernel virtual address? Because if you can't distinguish them, then that's going to be a pretty big problem. So that's the sharing problem. Now, the sharing problem is actually really easily solved, and it solves part of the bootstrapping problem, but not the whole thing. And that is we simply segregate kernel virtual addresses from virtual addresses of the user process. And we do that by creating a split of the virtual memory. And the most popular split is 50-50. All of the operating systems you use a 50-50 split, and it's the same 50-50 split pretty much. And that is the lower 50% of addresses are reserved for the user process, and that is why your stack appears in the middle of the address range, is because that is technically the end of the user virtual addresses. And then the kernel uses the upper 50%. So this is interesting because now we can differentiate between a kernel virtual address and a user process virtual address, not just in a software level, but at hardware. So your MMU, if your CPU is running in an unprivileged mode and the MMU sees a kernel virtual address, the MMU can throw an exception, because it will know, it's like, wait a minute, this isn't, I can't touch this address because CPU is running in a unprivileged mode, and this is a privileged address. So this is actually a really interesting way of separating the virtual addresses for the kernel and the user process. And this is also why your stack lives in the middle. It's because it's the end of the user range. Now, there are other operating systems which have used different ranges, like there's been 25-75 and, 1/3, 2/3 splits, but the 50-50 split is the most common one. And yes, that does restrict your user process to half of the available virtual memory. So if you have 32-bit virtual addresses, your user process can technically only use 2 gigabytes for its address space. And that's very, very restrictive. But I mean, if you're still using a 32-bit architecture, you've got bigger problems. If you look at today's, where we have 48-bit virtual addresses, then that means, you've got a lot more space. Because I think 48 bits gives you something like Oh, I don't even remember what it was anymore, if it was like 256 gigs or 256 terabytes. But either way, it's a lot. It's a lot of space. And there aren't many, regular user programs that actually need that much memory for their address space. Interesting. Now, the bootstrapping problem of how do you have the kernel run in virtual memory when it implements virtual memory. So for MIPS, it just uses a different address translation scheme for kernel addresses. So when the MMU sees a kernel address and we're in a privileged mode, it does essentially dynamic relocation. So that's pretty straightforward. All right, so I'm going to leave it here for today. Tomorrow we will review this topic and we will look at how OS 161 and the MIPS R3000 actually handle this and how kernel addresses get translated. And then we will talk about my favorite thing, which is going to be on-demand paging, because it's a super fun topic. So Thursday's episode 14, will be our final one for virtual memory. Yay. So we will see you on Thursday.
Please confirm. Woo! Oh, yeah. Next. Too easy. Oh, don't. No. Yes. 50%, please. Fuck. No. Fuck you. Shit, let's go fucking away. I'm rusty. Oh.
50,000 watts of fucking. 50,000 watts of fucking. 50,000 watts of fucking.
Okay, the answer to this guy is you. Eternal destruction. Quick. Thank you. Return. 3, 2, 1, go. Come on. Yeah. Oh, baby.
Gotta modify the code.